Hi, welcome to this clip going through a simple alkanes exam question. It focuses on cycloalkanes and their physical properties, and then goes on to look at radical substitution as applied to those cycloalkanes. Now, cycloalkanes have slight differences to normal alkanes in terms of their general formula, so you've got to be a little bit careful in this particular question. So the first part of the question gives you a bit of information about three cycloalkanes, including the boiling point, which allows you to see that as the size of the carbon ring increases, the boiling points go up. If you work out the molecular formulae from the skeletal formula, you can then work out some of the things you might want to say a bit further down. So you may recall about homologous series that it's a group of compounds that have similar function, same functional group, and therefore similar physical properties. But if you have worked out the molecular formula for each of those, you'll see that it increases by CH2 each time, and that's quite an important point to include. So the general formula for the cycloalkanes is CnH2n, because you can see that the molecular formula all obey that particular general formula. So you can use the molecular formula to come up with that. The next part of the question asks you to explain the increase in boiling points. So you've got to talk about the boiling point somewhere. That usually means something to do with energy being required to overcome either the bonds or intermolecular forces that are causing the boiling point to be at the level it's at. So let's have a look at what that might be in this particular case. There's a number of things you can say. Obviously, the greater the molecular size, the more the electrons are present, and more electrons mean more or stronger London forces. And also, the larger molecular size means greater surface contact points over those London forces can act. And that all leads to the final point, which is really important, that London forces require more energy to overcome during boiling, and you must make that point in order to score both marks. Now, there's a range of things you could say there, but that second point, that second mark, has to come from the London forces being overcome by more energy, and therefore, if you don't put that in, you'll only get 1 out of 2. So, going on to the next part of the question. All the products are cyclic. I'll just move myself out of the way there. And you can see that if we highlight that part of the question, that's something to tuck away for later on. So a specific instruction has been provided, and it tells you that the termination step down at the bottom of the table, there are 3 lines. So it says include all possible termination steps. I think the fact that there are 3 lines means that there's 3 termination steps. So you could read it like that and bear it in mind. Also, there's 5 marks on offer, so there's quite a bit of processing to do here. So from your recall of the radical substitution mechanism, you can come up with the initiation step quite easily. The propagation step has to include a new radical and a new molecule. There's usually 2 propagation steps, hence 2 lines, and the termination steps are basically all the different ways in which the remaining radicals flying around could be mopped up by bumping into each other and reacting. So your terminations have to be 2 radicals making a molecule. So, looking at the second part of the question, we're now going to look at homolytic fission. And it specifically says, explain why the initiation step is an example of this particular type of bond breaking. So you must make full reference to it and not just say something vague and in passing. So yes, a covalent bond is broken, but in doing so, 1 electron from the bond pair goes to each bromine atom, and therefore 2 radicals are made. So the equation using molecular formula for the reaction of cyclohexane and bromine in the presence of ultraviolet radiation to form C6H10Br2. There's actually quite a lot of information lurking in there, particularly the C6H10Br2. And this is a type of question that a lot of people actually get wrong because they don't realize what it is they have to work out. So the logic is that you know there's 2 hydrogen atoms substituted as a question says C6H10Br2. That means 2 HBRs. H2 is not made as the hydrogen radicals are not formed, so therefore the moles of Br2 must support this. So in the final part, any particular cyclic product is what you want. So any dibromo cyclohexane with the correct locant numbers, like any of these 4, will do the job perfectly. Okay, thank you for listening, and until next time, see you soon.